So in the last session we have seen about efficiency of a solar cell and SQ limit details. So in this session we are going to see beyond SQ limit techniques or techniques for achieving efficiency beyond SQ limit. Okay. So let us have a recap of what are the losses in a ideal solar cell. So we can see we have a thermalization loss. So a high energy photon, part of that is being lost as thermalization loss. Low energy photon is completely like getting lost, and there is a radiative recomposition loss due to non-zero temperature of the device. So some radiative recomposition is taking place, and then we have some other losses. So other losses are due to your entropy generation or due to your energy conversion loss. So irreversible reaction will have entropy generation. There is generation of entropy in irreversible reaction, and energy conversion is because our here basically a photon of high energy is getting converted into electrical energy at room temperature. So there is a temperature difference. So that is what getting the energy conversion loss. Okay. So if we have to achieve efficiency beyond SQ limit, we have to lower down these losses. Okay. So here main loss is thermalization and non-absorption loss, and radiative recomposition other loss also can be lowered down, and they are also having like 5 to 10% increment in the efficiency upon lowering them. So let us see the various techniques to lower down thermalization and non-absorption loss. So one of the technique to lower down this thermalization and non-absorption loss is multi-junction. So you can see out now if you use multi-level system instead of two-level system, if you use multi-level system or multi-junction system, you can have efficient absorption of higher energy photon or lower energy photon both at the same time. So this is effectively lowering down the non-absorption loss and thermalization loss at one go. So you can see an example of this as you can see here the example. The spectrum is divided into different energy levels, and then corresponding suitably matched semiconductor is being utilized for absorbing these different levels. So this is multi-junction solar cells. Other technique we can have is intermediate bandgap solar cell. So intermediate bandgap solar cell will allow us non-absorption loss reduction. So non-absorption loss, those low energy photon can be absorbed. And you can see here the transition from valence band to intermediate band, and then intermediate band to condension band, and there is a direct transition from valence band to condension band also. So all those non-absorbed photon are being absorbed. Okay. So an example you can see here, the example I will show. You will see the example here. In this system you have a p-type emitter, n-type base, and in between you have a n-type layer. Okay. So this n-type layer have in between some quantum dot arranged in between. Okay. So this energy band diagram you see here, this is the p-type emitter which is highly doped, and then this is the n-type. So all the band bending is in the n-type region, so this band bending region, and then this is the n base. So this is the n base, and you have a quantum dots in between this n gallium arsenide layer. So this and these quantum dots, they are making a quantum well, their energy levels, and then they are also having a Fermi level EF. Okay. So they are also having a Fermi level. Okay. So this is there is a transition from valence band to condension band directly in N, and there is a transition from valence band to intermediate band, and then intermediate band to your condension band also. So all below energy photon are also being absorbed using this your intermediate band system. Okay. So this is again a useful technique to achieve efficiency beyond SQ limit. Okay. And then there is one technique which is hot carrier solar cell or multiple temperature solar cell. So a high energy photon is being absorbed, and then that high energy photon generating a high energy electron pair, and that electron is, instead of getting relaxed to the minimum of conduction band, it is getting collected at this high temperature itself by a energy selective level. Okay. So this will be known as hot carrier solar cell. Okay. So this will generate out high voltage output and reduce out the thermalization loss. Okay. Then you have another system which is up conversion, down conversion. So those photons which is higher energy photons, they can be absorbed by one particular layer, and then that layer is emitting two number of photons of lower energy. So this is down conversion. Okay. And then these photons are being absorbed by your two-level system, and all those photons which are below energy photon, they will be absorbed by the separate layer, another separate layer, and then upon absorption of multiple low energy photon, high energy photon being absorbed, and then that is being absorbed by your two-level system. So this is your multi-spectrum system. Okay. Or up conversion and down conversion system. So this will also reduce out your thermalization and non-absorption loss. Then we have another one system which is two photon absorption. So two photon of low energy, they are absorbed simultaneously by electron, and then electron make a high energy jump. Okay, so two low energy photon are enabling electron to jump over or to make a transition from valence to conduction band. Okay, and then you have a impact ionization or OJ generation. So OJ generation is a one high energy photon. One of the high energy photon is being absorbed, and then that instead of thermalization, this energy directly released as a radiative energy. Okay, so this radiative part, the radiative energy is being absorbed by the another electron, and then that electron also make a transition to the conduction band. So instead, we are having a two electron hole pair generation by one high energy photon absorption. So this is impact ionization or OJ generation. So these are all the techniques for lowering down thermalization and non-absorption loss. Now you can have some other techniques to lower down other losses. So radiative decomposition is the intrinsic loss which cannot be avoided, but your entropy generation and your energy conversion loss, that can be controlled, or that can be like optimized. So we have some techniques we'll see now here. So in the summary you can see all the techniques which are giving efficiency beyond SQ limit. You can see gallium arsenide with 29%, or the SQ limit efficiency is 33%. Okay. So now in this SQ limit, what you do, you put angle restriction so that you avoid high entropy generation. Okay, if you avoid high entropy generation, then you can have like SQ limit for single junction is 41%. So that is angle restriction is being put by achieving complete maximum concentration. Okay, so that's one thing. Then if you control in this SQ limit, you control only thermalization and non-absorption loss, then the single SQ limit efficiency can go up to 68%. Okay, so by controlling only thermalization and non-absorption loss. So this can practically achieve by infinite tandem at 1 sun. So this is SQ limit at under 1 sun. Okay, this is infinite tandem at 1 sun. And now in this infinite tandem, efficiency, maximum efficiency at 1 sun, if we put again here also angle restriction by having maximum concentration of light, the efficiency will again go up to 86.8%. Okay, so that is the maximum achievable efficiency by any practical mean. Okay, so the practical mean here is infinite tandem at maximum concentration. So you can see out, you have a down conversion efficiency which is 39.6%. You have multi-junction for two junctions, 42%. You have multi-excitation generation, which is 44%. You have up conversion, so alone up conversion, which is giving 47%. You have multi-junction with their respective energies. You have intermediate band gap for avoiding non-absorption loss, the efficiency is 63%. You have hot carrier for avoiding thermalization loss, the efficiency is 66%. And you have efficiency of 86.8%, which is the maximum efficiency achievable by any practical mean. Now you are seeing some Carnot efficiency. So Carnot efficiency is the energy conversion limit. If you see sun is at 6000 Kelvin and Earth is at 300 Kelvin. Okay, so the efficiency will be given by, I will write it down. So efficiency neta will be given by 1 minus T cold by T hot. So T cold is room temperature, which is 300 Kelvin, and T hot is sun temperature, which is 6000 Kelvin. So you put out this value and you get the values. So 1 minus 300 by 6000 Kelvin. So that is giving out roughly 95%. That is the Carnot efficiency limit. So basically energy conversion from hot temperature to lower temperature. So that is the maximum achievable efficiency. But this is only theoretical. And if you take care for such reaction, for such energy conversion, if you take care of entropy generation, then it will give you Lenz's work limit, which is 93%. Okay. And if for our practical mean, for any practical mean, the achievable efficiency is only 86.8%. So it is the almost 13% loss is going into these losses, energy losses like Carnot losses, entropy generation losses, and your emission losses, radiative recombination losses. Okay, so those are the losses. So by any practical mean, we have the efficiency of only 86.8%. So this is all about the SQ limit, how to achieve efficiency beyond SQ limit. So in the next session, we will see about radiative recombination losses or non-radiative recombination losses in our practical devices.